Okay, so it has started recording. Very good. Yeah, I hope today power doesn't go. Yesterday, I was talking for maybe 1 or 2 minutes without noticing that the power had gone. So, yeah. So, but it did not affect the recording. I did check that part of the recording. It was fine. So, okay, some people are asking today's lecture is not part of the quiz, etc. Yes and no. Formally, no, because whatever we have covered till yesterday is the theory part of the thing. But as you see, today we are not doing any new theory. Okay, so in that sense, today's lecture also you should know because there's no new theory coming here. We are only using the theory that we have covered till yesterday in order to do a bit more. So in that sense, these things, anyway, as you will see, there's nothing new today. Okay. It's only some methods, no new theory. Anyway, let me start sharing the screen and let's start. By the way, Tuesday is the day where you have immediately a later class, no? Monday and Thursday, no. You have a class soon after this lecture, right?
Yes, sir.
Tuesday, I should be even more careful than usual case. But yeah, let's start the lecture. So you can, one of you can just confirm that you can see the.
Yeah, we can see the slide.
Yeah. So as I said, there is nothing new today. For example, constant coefficients, you can guess, no, what do I mean by this? Anyway, we have been discussing second order linear ODEs in standard form. So what's the meaning of constant coefficients?
All the coefficients of.
Yeah, all the coefficients are just numbers, constants. Okay, so there's nothing new today. So you can't say that, we can't ask a question based on constant coefficient because that's already done. I mean, we are only, specializing. And Cauchy Euler, though the word may be new, this also we have already discussed. Already in, your tutorial 1, question 5 had 2 parts, right? Question 5 and tutorial 2 had 2 parts. One was about constant coefficients and one was about Cauchy Euler. Maybe the word was not there, but why a name is important. How you solve this was already discussed. So I'm only recalling what you have already done in your tutorial. So in that sense, there's nothing new today. All this is really part of the syllabus. Okay. So anyway, just pay attention. It will be just, formally writing down something which you have already done in the way of examples. Okay, so let's start. So let's quickly recall very quickly what all did we do yesterday. So yesterday, would you say that we had a little bit more theory than on a usual day? Is that your impression about yesterday's class?
Yes, sir.
Yeah, so a bit more linear algebra came yesterday, no, than usual, right? So let's quickly recall. So first of all, we defined the Wronskian. What was the definition? If you have f and g differentiable functions, then the Wronskian is also a function, Wronskian of f comma g at the point x. X is a variable as the determinant of the matrix fg, no, not fg, fx, gx, f prime x, g prime
minus gf dash.
2 by 2 matrix. And this had nothing to do with differential equations. Given any 2 differentiable functions, you can define the Wronskian. Okay, but it played a role in differential equations. And if f and g are solutions of a second order linear differential equation, then we proved the Abel's identity. So yesterday I did not state the word, I typed it in chat, but of course you know what this is. So what is the form? If f and g are solutions of y double prime plus px y prime plus qxy equal to 0, what is Abel's identity? It says that w of fg at x equal to w of fg at some point a times, I'm not very good in memorizing. Can you tell me e power?
Integral a to x py.
Was there a minus sign?
Minus sign. Yes, sir.
Minus, no? Minus integral a to x px
by
dx,
dy.
is that correct?
Sir?
Px dx?
pt dt kind of y, right?
Minus integral px dx, right?
Yes, sir.
Yeah. And what was the main idea of the proof? So w is given to you. So it is fg prime minus f prime g. Then what did you do? You took one more derivative, W, right? W prime you took, and then some G double prime, F double prime came. Then you use the fact that these are solutions of the given differential equation. So F double prime and G double prime you wrote in terms of P and Q. And when you plugged all that in, you got a very simple differential equation for W. What was the form? W prime equal to minus PW. Is that correct?
Yes.
So that's a separable equation, and therefore you solved it. So the main thing to remember here is only P mattered, not Q. Right? Only P mattered, not Q in Abel's identity. And one very useful fact because of Abel's identity is if the Wronskian vanishes at one point, then it is identically zero. Not for any two functions, but for two functions which are solutions of a second order homogeneous linear differential equation in standard form. Let me say coefficients continuous, though for this particular thing, maybe integrable was enough. Okay. So this was Abel's identity, and I quickly recall the proof. What about how is linear dependence and independence connected with Wronskian? We proved a result that if f and g are, we first of all proved that if f and g are dependent, then Wronskian is zero. Nothing to do with differential equations, just calculus. If f and g are dependent, then Wronskian is identically zero. And then we saw that the converse is not true. Wronskian zero does not mean f and g are dependent. We saw a counter example. But if f and g are solutions of a second order linear differential equation in standard form, all those conditions, then it is if and only if linearly dependent, if and only if Wronskian is zero. So if Wronskian, if linearly dependent, then of course Wronskian is identically zero. On the other hand, if Wronskian is zero at any one point, then of course Wronskian is identically zero. And then we concluded that f and g are linearly dependent, provided f and g are solutions of a second order linear homogeneous differential equation in standard form with continuous coefficients. Here continuity is important, with continuous coefficients in standard form. Okay, and we saw the proof of this result also. What was the main idea of proof here? Suppose f and g are given to you. Suppose you know that they are solutions. Without loss of generality, you can assume that one of them is not identically zero. So if f is not identically zero, then in particular f is non-zero at one point, and in particular f is non-zero throughout an interval, sub-interval, because of continuity of f. And then you consider the function g by f, that is differentiable. You take its derivative, and derivative will have numerator Wronskian, which is identically zero because it is zero at some point, therefore it is identically zero. So you have got that g by f, derivative of g by f is zero. So g by f is a constant. And then you, if the constant is k, you consider the function g minus kf, analyze that, use the existence uniqueness theorem, and conclude that g equal to kf throughout your interval. So g and f are linearly dependent. This was the quick proof. Okay. So these are all very beautiful ideas, bringing a little bit of linear algebra and the full power of the existence uniqueness theorem. And we also proved the dimension theorem yesterday. Assuming the existence uniqueness theorem, I gave you a proof verbally of the dimension theorem. So the only thing that we have not proved is, can you tell me what we did not prove and we may not prove?
Uniqueness theorem.
Existence uniqueness theorem. Okay. So that we did not prove, but you should be able to use it in all possible ways. Okay. So now let's do a bit more and then do the constant coefficients and Cauchy Euler, and that will be the all that I'll cover today. And then we have a class on Thursday also, where I might do some new theory. So I don't exactly remember what is Thursday's topic. As I told you, I also prepare the very last minute. So what is coming in the next lecture, I don't know today, because I prepare for Thursday class, I prepare on Wednesday night or Thursday morning. So, but we will see. But if there is a new theory coming, of course, that's not part of Friday's quiz. Okay. So actual syllabus is still yesterday, but I am saying, what we are doing today, there is nothing new. So in that sense, this is also there. You should be comfortable with what we do today, because this is something that you've already done in tutorial. Okay, so we have been looking at second order linear homogeneous ODE like this, and there is no general method to find a basis. But if we know one solution, so this is the only extra thing that I'm doing today. If you know one solution, then you can find the other solution. Okay, so what is the method? Such that both are linearly independent. So let's do that. So one solution someone has given you, or you could guess, or somehow you got one solution and you would like to know what the other solution is based on that. Okay, so in some question, if you can use this method, feel free to use it. Don't say that it's outside syllabus. Maybe you don't have to use it in order to solve it. In that sense, that is part of the syllabus. But if you can use it, nothing stops you from using something else also. The world of mathematics is there for you to use if you know. Okay, so we will not penalize for you using something else which we haven't taught or any such thing. You can use whatever is true. Okay, so to find such a gx, we are going to experiment. Suppose there is a gx of this form, a function times fx, vx times fx, and now we will choose a v such that f and g are linearly independent. Okay, so we are just experimenting, and this experiment is going to work nicely. So can v be a constant? First of all, can vx be a constant? Please tell me.
No.
No. Why? Because you would like it to be linearly independent. So it cannot be a scalar multiple. So v cannot be a constant. Now for g to be a solution of the given ODE, you are experimenting, will such a thing work? So suppose there is something like vxfx, and for this to be a solution, you can plug it in, right? G double prime plus px g prime plus qx g equal to 0. And you can find g prime and g double prime. Assume v is twice differentiable. So you will get vf twice double prime plus px vf prime plus qx vf is 0. What will be my next step? My next step is writing down this and writing down this by, what do you call, product rule or chain rule? Product rule, no? Derivative of the product.
Yes, sir, product.
Yeah, product rule. So I have put this all together here. So should I explain one by one? No need, right? What I am doing is vf double prime. So that is vf prime prime. What is vf prime? Vf prime plus v prime f. So vf prime plus v prime f prime plus p times vf prime, that is this, plus qvf, which is I have taken, now I should call this chain rule, right? Yeah, so I don't remember which is which.
Sir, still
Anyway,
product.
you know how to do this. Chain rule, I think. So this is v double prime plus v prime f prime plus v prime f prime. So I have written 2v prime f prime plus vf double prime. So this much plus this plus this. Now I have club terms. So v.
Sir, v double prime f, right?
Sir, you missed it in the second line, but it came back in the third.
Okay, okay, good. So this is v double prime f. Yes. So please tell me at the end to correct this typo, or I will remember. So one typo, very good. So v double prime f, and everything else is okay.
Yes.
Okay. So now I have taken v as common factor. So v times qf here, v times pf prime here, and v times f double prime here. Okay. So v times this plus v prime times 2f prime plus pf here, and v double prime f. Yeah, the missing f I have written here. Okay. So typo is in this line only. Now what do you see? What do you know about this bracket?
0.
0. So that is very good. So this is 0 because f is a solution. Therefore, what did you get? You got a nice separable equation. V double prime f equal to minus of v prime times 2f prime plus pf. So v double prime by v prime is minus of 2f prime plus pf divided by f. Agree? This you are getting because this is 0. Okay. So this equal to minus 2f prime by f minus p. Okay, can you solve this for v? This is a differential equation,
Yes,
v
sir.
and, right? This you can easily solve because it's separable. So integrate, what will you get? What is the integral of this left hand side? Log of
V prime.
v prime or mod v prime, whatever.
V
Log
prime.
v prime. And what is the integral of this?
Log of f.
Minus 2 log f, right? Minus 2 log f, and this will be minus integral p dx. Minus integral p dx. So log mod v prime is log of 1 by f square, that is minus 2 log f. So log 1 by f square minus 2 log f minus integral p dx. And therefore you have solved for v, right? V equal to, so you take exponential and then you integrate in order to get v. So you have got a v. You have got a candidate v so that vf will be a solution. Now the only question is it independent from f?
Hello,
V
sir.
times f, is it independent of f? How do you check that? It's already a solution. Now the only question is vf and f together, are they linearly independent? What is one method from yesterday to easily check for linear independence?
Using Wronskian.
Wronskian.
Just take Wronskian, okay? Just take Wronskian. If Wronskian is not vanishing, then you have concluded. Now Wronskian will not vanish. Miracle, not miracle. I mean, it so happens. So claim f and vf are linearly independent. Proof enough to check. You have already said the word Wronskian. Okay. So w of f comma vf I am taking, which is f times vf prime minus f prime times vf, and in this f prime times vf cancels, so this is just f square times v prime. Second term cancels. So f square times v prime, and what is v prime? What is v prime? V prime is e power minus integral p dx by f square, right? V prime is the integrand here. So v prime is that, substitute, it is f square times the integrand there is e power minus integral p dx by f square. F square cancels, so you get exponential of something. But exponential is never zero, right? Exponential is never zero, no?
Yes.
Yes, sir.
Yeah. So you have concluded that the Wronskian is never zero. So good for you. So you have shown that f and vf are linearly independent. Good method, no? So if you somehow know one f, then you can find one more thing so that they are linearly independent. So even in that problem that you discussed just before we started recording, if you have somehow guessed e power x times x square is a solution, then you can find out the other solution by this method also, right? One of you told me that one you could guess easily, then the other you could have found out by this method, which I was not thinking when I said the question, because I did not remember that this is coming now. Okay, so there are other ways also to guess, but this also will be helpful. Now we
Sir,
are
but
going
this requires P to be continuous, right? P and Q.
yeah. So what is so in all such questions where there's a problematic point, your method has to be, see, theory will not help you. So your method has to be restrict, like the Cauchy Euler problem that we did yesterday in detail. You restrict yourself to a good domain where 1 by x makes sense, and there you do your analysis, get your solution, and then use common sense and calculus to see whether that extends or not. This is our method, no? Even for that problem, if e power x by x is coming, that is well defined in some subinterval, right?
Yes, sir, I get it.
So v being continuous, etc., we will do only on some subinterval when you can apply the theory. After all, if problematic point is there, no theory is helpful. You have to, use your common sense. Common sense, I'm using this word common sense just for, your previous mathematics background. Okay. Agreed?
Yes, sir.
Yeah, okay. So shall I go ahead? Now we are going to apply this particular little bit of theory that we have done. But again, what theory? Nothing. This is theory from yesterday only. It is just, one experiment using Vx times Fx and using yesterday's theory only. So whatever I'm doing is yesterday's syllabus only. I mean, yesterday's, whatever we have covered yesterday. Okay. Now we are going to apply this to constant coefficients and Cauchy Euler. So let's do one example and then we will do more theoretically, but it's all very easy. Today's must be the easiest lecture. Yeah.
So in the previous thing, if v of x is not a constant, g of x will be independent of f of x, right?
No, you can't say, no, it is not. See, finally you are right. So I cannot give a counter example to contradict because we have proved that. But how do we know fx, gx and vx fx? Fx and vx fx may be dependent, no? Well,
So
finally it's
then
not.
How
that
will they
will
be?
make
Sir, if v is not constant, then we can't like.
No,
I mean,
no. See, for example, we had this example, right? The function x square. Suppose fx is the function x square. And suppose gx is the function x square to the right side and minus x square to the left side. Now ask the question, can you write that function as vx times fx? Of course you can, no?
But V wouldn't be a constant, right?
Yes, sir.
V is not constant, no? V is not constant. V is 1 on the right side and -1 on the left side.
So they are not dependent as well. So it's not contradicting anything.
It's not contradicting.
Because if they were dependent, then g of x.
Okay, correct. Yeah.
Like,
So we want to say that Vxfx is independent of Gx. Yeah, correct. So what you are saying is correct. Of course, I will not get a counter example because after all we proved that. But you still need a proof, no? You need to give some argument, no? You can give another argument without Wronskian, but you have to give some argument, right? You are saying it's absolutely obvious?
We can say that if Vx, Fx and Fx are independent, then V must be constant.
Yes, you can prove that. Yeah, correct. You are right. You can prove that. So you take A Fx plus B Vx Fx equal to 0. And then you have to show that if Vx is not a constant, A is 0, B is 0. Yes, of course you can do that directly. So then can you tell me why I introduced Wronskian here?
For the purposes of the proof, I guess.
For the purpose of the proof also, you could have given a direct linear algebra proof. You could have taken...
To show that V is not constant is not that easy, but using Wronskian we can show that.
Only reason why I use Wronskian is I like this proof because, you know, the nicely Wronskian, it is just to use, you know, our Wronskian knowledge once again. You could have proved it directly using basic linear algebra. Okay, you did not need Wronskian, but I really like this proof because, you know, the way you solve it, you are also getting, okay, anyway, you know, you are getting an expression for V because you want it to be a solution. So in that sense, this is important. And finally, to show this linear independence, Wronskian not being 0, it is coming out very nicely here. So I like this. F square and F square nicely cancelled and you are getting exponential and you know that it is never 0. So it is matching nicely with whatever we have done yesterday. Okay. For that reason, I introduced this proof. You could have proved it directly also. Okay. It's only a linear algebra statement.
Sir, but actually proving V is not constant directly doesn't seem to be easy. This is probably easier.
Okay. So you have to try. Yeah, proving V not constant is, if not directly easy. Yeah, so I have not done it. So you try.
Okay, actually, I think you can quite easily show. I mean, we can take derivative of V.
There must be a way. I don't think it's a difficult thing. So when V is not a constant, Fx and Vxfx are linearly independent. You can have many different proofs. Here is one proof, and this proof is nice because, you know, you see nicely how yesterday's knowledge is coming into picture. Okay, that's all.
That V is constant and vacation is 0. V prime 0.
If V is constant, of course, it is linearly dependent. No, a scalar Vfx is a scalar multiple of f. So of course, it's linearly dependent. And this proof, our proof will not work because if V is constant, then V prime is 0. So you cannot do this step. Okay, so this also doesn't work. Okay, so anyway, you have many proofs. Let's do one simple example, and then next slide I will say that what this example is actually a little bit of theory. So in this case, write this in standard form. You're assuming x is positive or something. Write it in standard form. And then how do you try this thing? How did you try this in the tutorial? Such a question?
We assume a solution of the... We assume a solution to be...
You assume that, yeah, so in this case, you can observe that x is a solution, but more generally, how did you do such a thing?
If you take x power n, we'll directly
X to power n.
Yeah. You try x power m, you will get a quadratic in m and you solve for m, right?
n equal to plus or minus 1 we'll get.
Yeah, so and you will have to analyze 3 cases, both real roots, both complex roots, and distinct real roots, equal real roots, and complex roots. This is what you have to analyze. But in any case, here fx equal to x is a solution. So assume that Vx is another solution. And then you can do what we have done. Vx, this is the formula, or you can do it directly. So I don't know whether formula is better or doing it directly is better. It depends on your temperament. If your memory is so good, you can use the formula. If you don't trust your memory fully, do it from first principles. Because, you know, missing a minus sign may be disastrous. So unless you remember very correctly, it's best not to use a formula. Okay.
Sir, just assuming a solution of the form x power m, we can obtain two independent solutions directly because m will give, it will give us two values for m in this case.
Yes. Of course, you will get, and that's what we are going to do now. But this is an example to illustrate what we discussed just now. Okay. Of course, most of these questions will have many different ways of solving. So I am just picking one solution. So you do this, and this is e power minus integral dx by x, because p has to be, in the standard form only you take p. So p is 1 by x. You are not applying it here. You are applying it in standard form. That's important. And this is e power minus log x. That is 1 by x. So you got 1 by x cubed dx, and you got some answer. So you multiply by this, and therefore you got any solution to be of this form. You could have done it directly. You will get a quadratic where m will be +1 and -1, right? If you substituted x power m and solved it, you would have got a quadratic in m, and the roots of that will be +1 and -1. And you would have got it directly also, but I am applying this method. Okay, so we have developed enough theory now to find all solutions of constant coefficients. Maybe you can tell me, what will you do here? Again, this came in the tutorial problem. What is your substitution for constant coefficients?
E power lambda
Like
x.
E power lambda x, and when you substitute, you will get a quadratic in what?
lambda.
Lambda.
So see, it's nothing new I am teaching today. You know this, okay? So a second order homogeneous, this thing with constant coefficients. Suppose e power mx, I'm calling m instead of lambda, is a solution. So you got m square e power mx plus pm e power mx plus q e power mx is 0. E power mx is never vanishing. You can cancel it. So you got a quadratic, and this is called the characteristic equation, or sometimes the auxiliary equation of the linear homogeneous ODE with constant coefficients. Solve this. What are the roots? Minus p plus or minus root of p square minus 4q by 2. And what are the three cases now that we will analyze?
Real distinct roots.
Real distinct case 1, real equal case 2,
and then
and complex
conjugate.
Yeah, complex and its conjugate. Can the two genuinely complex roots be equal? Or should we analyze equal complex roots and distinct complex roots?
No, if p and q are real, then the roots cannot be complex roots cannot be equal. I mean, the real roots will be all that will.
Correct. So non-real roots cannot be equal, because if a plus bi is a root, then a minus bi is the other root. So if they are equal, then b is 0, which case we have already seen, because that's equal real roots. Okay. So let's analyze case 1. m1 and m2 are not equal, distinct real roots, in which case p square minus 4q is positive, right? If these two roots are distinct, then p square minus 4q is positive, because it's also real. And so m1 and m2 are distinct real numbers, in which case e power m1x by e power m2x is not a constant function, and therefore what do you conclude? E power m1x and e power m2x are linearly independent. These are linearly independent, and so the general solution of this will be, so you have already got two independent solutions. Do you need to look for more solutions?
No need, sir.
No need. Why?
They form the basis. Their combination of.
Yeah, because of dimension theorem, you know that there are only two linearly independent solutions, right? Basis dimension is 2. So once you get two linearly independent solutions, then you know they will span the whole other thing. Therefore, a general solution is C1 e power m1x plus C2 e power m2x. Agree? So case 1 is done. Case 2, m1 equal to m2. So that means p square minus 4q. Is this what is called the discriminant?
Yes, sir.
Okay. So p square minus 4q is 0. In which case, what is m? M you can find out, no? Because m is minus p plus or minus 0 by 2. So m1 equal to m2, which I am calling m, that is minus p by 2. So m is minus p by 2, and therefore e power minus p by 2 times x is one solution. But how do you get the other solution?
Using the analysis we did sometimes.
Using the analysis that we did. So assume that there is a solution of the form Vx times e power minus px by 2. Plug it in. So Vx will be, I am remembering the formula. And tell me, how did I get this? If you tell me that, then this theory is done. Why is this a linear
P is a
function?
real, means
P
it's
is a
constant.
real number and P is a constant. P is a real number. P is constant. So P comes out. And P comes out. What is integral dx? X. So this is numerator is e power minus px. Denominator is also same thing. So that cancels. So this is just integral dx. And integral dx is constant times x plus another constant, right? No, why did I
The
write
constant should
AX?
not be there. A
Why
should
did
not
I-
be there.
Why did I write ax and not just x? Can you tell me?
So it's because that e power minus pdx gives a constant.
Yes, yes. Here there is a constant. Absolutely. So this is integral dx. This is minus integral dx, which is minus x plus a constant. So this is e power minus px times a constant. So this is that constant, let me call a. So this is integral a dx, which is ax plus another constant ax plus b. All of you agree? So you will get vx to be of this form. So you can choose any one vx, no? So what is the easiest function of this form? B equal to 0 and a equal to 1. So I have chosen vx to be x. Therefore, gx is x e power minus px by 2 is a linearly independent another solution. So a general solution will be of the form a constant times e power minus px by 2 plus another constant, possibly another constant times x e power minus px by 2. Is there any doubt on this slide?
Sir, I had one thing.
Yeah.
If I combine these two, a plus bx of e power minus px by 2 are coming now.
That is okay.
Again, it is becoming this v of x e power minus px by 2 part only.
No. When you write general solution, only constants are allowed. Dx is not, x is not a constant.
Yes, sir. I'm saying this again becoming like the g of x one, no?
That's okay, no? No. We are talking about general solution. See, this was a method to find just one solution which is linearly independent from the given fx. Okay. Once you get one solution, what is the general solution? Now, do you agree that e power minus px by 2 and this function x e power minus px by 2 there that forms a linearly independent set?
Yes, sir. By
Both are solutions and they are linearly independent. So it's a basis, no? Therefore, any basis means what? Any other thing is a span of these two, right?
Yes, sir.
So any other solution will have to be of this form. A constant times the first one plus a constant times the second one. You can also write this as a plus bx times e power minus px by 2, no problem.
Okay, sir.
So then you are saying that, okay, your general solution is a multiple of one solution. That's okay, no contradiction. Because A and B are varying, no? So general solution is a general solution. Okay, so up to you. You can write that way also. Is the confusion cleared?
Yes, sir.
Okay, so what is the case 3? What is case 3?
Complex roots.
Complex. Okay, complex.
Okay.
So M1 not equal to M2 and it is a genuine complex number, meaning it's not a real number. Okay. So in this case, p square minus 4q will be negative, right? The discriminant is negative. And let us write M1 to be a plus IB and M2 to be a minus IB, and we are assuming B is non-zero. That's why it's case 3. If B is 0, it was already case 2, which we have done. Okay. So M1 is a plus IB, M2 is a minus IB. So what is e power M1x? E power M1x is e power a plus IBx, which is e power ax times e power IBx. But what is e power IBx? See, you would like every function to be real functions, not complex. So I don't like I because that's a purely complex number. So what is e power IBx in terms of real functions? What is e power
Cos
IX?
theta plus I sin theta.
Absolutely. So it is e power ax cos bx plus I sin bx. Let me also check what is e power m2x. It will be e power ax times cos bx minus I sin bx. But I don't like these. See, I don't see this is. It is true that these two form a basis, but I don't like this notation because I is coming and we don't have complex analysis in this course. So how do you rewrite this so that you get two real functions which will form a basis? Can you tell me the basis?
Add two equations.
Add and subtract. So add and subtract, we are interested only in real valued functions, and therefore I take fx to be addition, and that is e power ax cos bx, and gx to be the subtraction divided by 2i, and that is e power ax sin bx. So this is, and these two are independent, you can easily check, and therefore, yeah, this is not a constant function, so they are independent, and therefore the general solution is of the form e power ax times an arbitrary constant times cos bx plus an arbitrary constant times sin bx. Okay, so we have fully analyzed constant coefficients. Now we are going to do
Sir,
this type. Yeah.
regarding the complex numbers, I think we can a useful result that we can use is if we have this kind of a real differential equation, linear real differential equation, and we obtain like we look for solutions that are from R to C, then this R to C functions can be written as f1 plus I f2, where f1 f2 real. So if we
That's
get a
exactly
solution,
what,
then we actually get two solutions, because f1 and f2 will both satisfy. That can be seen in the linear differential.
Correct. That's exactly what I'm doing here. Okay. So if you allowed the complex valued solutions, then you can say that these two itself are the answer. E power m1x and e power m2x are answers. But we are interested in real valued functions, and therefore I have converted it like this, exactly as you suggested.
Okay. No, I was pointing out that the real part and imaginary part separately will give you solutions.
Correct. That's exactly the argument here. This is in order to get real part, and this is by definition the real part, and this is by definition the imaginary part. So whenever you are pointing out that whenever you get a solution which is complex valued, just take the real part and the imaginary part. Yes, that is correct. That will work. Okay. So Cauchy Euler, same analysis, exactly same analysis. I don't need to do it because it's exactly the same analysis, but let's do it so that it's part of the slides. So as you told me, what is the substitution here? Earlier you substituted e power mx. Now what is the substitution?
X power m.
Plug in x power m. By the way, these equations are called Cauchy Euler. And yesterday's my tricky question was an example of a Cauchy Euler equation in an interval containing 0. In an interval containing 0, this is problematic. But let us assume that x is positive, so there's no problem. And assume y x power m is a solution. So when you plug it in, you get a quadratic in m again. Because x is positive, you can cancel this, right? Or x is negative also, you can do the analysis. X should not be 0. As long as x is not 0, you can cancel this. You get a quadratic in m, and you can find out its roots. And this is the auxiliary equation or characteristic equation or whatever you call. And the roots are your usual formula, minus b plus or minus root of b square minus 4ac by 2a. So you have got this. How many cases we have to analyze now?
3.
3, exactly like earlier. Case 1, distinct real roots. So the question is x power m1 and x power m2 are linearly independent? Answer is yes. And therefore the general solution is c1 x power m1 plus c2 x power m2 in this case. Okay. Case 2 will be equal real roots, and in which case you will get m1 to be equal to m2, and that is equal to 1 minus a by 2, right? 1 minus a by 2, because this is 0. So 1 minus a by 2, in which case we will use that method. So x power 1 minus a by 2 is a solution, and the other solution we will assume there is a solution of the form vx times fx, and I have done exactly what we have done earlier. And so I'm doing it slightly in this different way. So again, is there a mistake here? Should it be v double prime f? No, this is correct, no? There's no typo here, right? No, there's no typo here. And you could have applied the formula also. So you got something, fx is this, so substitute. So this is something, there's no point in my reading it out, no? What further thing I'm doing by reading it out? It is this substitution, and you substituted, you could have applied the formula directly. This is all that we have done already, and you will get something like this, and that is v double prime by v prime equal to minus 1 by x. You could have applied your formula directly, right? What is this formula? V prime equal to vx is this formula you could have applied directly also, no problem. Okay, just for fun I did it, I derived it again. You can do it either way. And where are we? You got this, you found out V. So what is V? What is V from here? So log V prime is minus log X, that is log 1 by X. So V prime is what? No, did I make a mistake? So log V prime is what?
Minus ln X.
Minus log X, that is same as log 1 by X. So V prime is 1 by X. So what is V?
V to
minus
ln X.
ln x square.
V is log X. V is log X.
We log x plus c.
Yeah, there may be many constants, but I'm ignoring all the constants because you want only one function V. So you can take V to be log X, V to be log X, and therefore you got the other solution to be log X times X power 1 minus A by 2. So repeated roots also done. So general solution is an arbitrary constant times X power 1 minus A by 2 plus an arbitrary constant times X power 1 minus A by 2 log X. What is case 3? Complex roots. So case 3, complex roots. And I'm not doing it. I leave it as an exercise for you to check that the general solution is given by exactly like earlier. Cosine and sine will come when you replace I. So general solution will be if A plus, what is A and B here? A and B, are the A and B given in the, this is the question, right? A is the coefficient of y, xy prime and B is the coefficient here. So you analyze complex roots. This being negative, write it as, s plus ti and analyze it. And let me leave it as an exercise for you to check that in the complex root case, you will get the general solution to be x power a c1 cos b log x plus another constant times sine b log x with c1 and c2 arbitrary real coefficients. And this is the last slide. Maybe I went a bit too fast, but it's okay because there's nothing, conceptually there was nothing difficult. So what did we do today? Just to summarize, we recalled whatever we did yesterday, and then we did this small thing. If you somehow know one solution, how to get the other solution by multiplying with Vx and doing some small calculus. And we applied this method to constant coefficients. We wrote down the auxiliary equation. We had to do 3 cases: distinct real roots, equal real roots, complex roots. And then we did it for Cauchy Euler. Constant coefficients, the thing that you tried is e power lambda x, and Cauchy Euler you try x power m. You will get a quadratic in m and analyze 3 cases: distinct real roots, equal real roots, complex roots. In all these you can write down. So the moment you get the second solution, then you are done, because dimension theorem tells you that the solution space has dimension 2. So the moment you get 2 linearly independent solutions, you can stop. These are all assuming that you are in a nice domain. That is very, very important. For constant coefficients, of course, any domain is nice, but Cauchy Euler, it is important that 0 is not in your domain for you to do this analysis. Okay, so let me stop here and stop sharing and stop the recording as well.